So remember what we were doing? We were talking about alternating series. We have this thing, Leibniz's test. Leibniz's test, which says that if you have a sequence, right, a positive sequence, and it is decreasing, positive, decreasing sequence, and the limit is 0, right? Then the infinite series -1 to the n plus 1 a sub n actually converges, right? Right, and we explained why this happens last time, right? The picture was wait, what was the idea? Is anybody capable of stating why this series converged? Does anybody remember? Anybody talk about it? Like how did it go? Anna, do you want to talk about it?
It was kind of like there was like a point, like 0, and then you would add some A1 to the point, and then you would subtract an A2 that was less than A1, and then
add on.
Keep going where it was never as much as the previous one.
Right.
So eventually it would be
Right. So what was the thing we looked at? So what you're talking about is look at the sequence of partial sums, right? Look at the partial sum sequence. Look at the partial sum sequence. Right? Look at the partial sum sequence. Right? Here's S1, right? You've added on A1. First you add A1, that's your first guy, right? And then you say, okay, my S2 is going to be the first two terms, A1 minus A2, right? S3 is going to be A1 minus A2 plus A3, and then you subtract off A4 to get this S4, add on A5, etc., right? And as you say, right, the distance that you go back, the distance you go each time is less and less, right? Because this is a decreasing series, decreasing sequence, right? And so you get this sort of bouncing back, right? This thing that sort of bounces back and forth. And what you notice is that you observe that the even guys, the even partial sums, S2, S4, S6, etc., are increasing, and the odd guys, 1, 3, 5, etc., are decreasing. Right? The even guys are increasing, the even guys are increasing, the odd guys are decreasing. Right? And further, you also notice that any odd guy is an upper bound for the evens, and any even guy is a lower bound for the odds. Right? So you also observe any even guy, so any S sub 2n is a lower bound for the odd partial sums, right? Any S2n plus 1 is an upper bound. For the even partial sums. Right? And so each of these things is going to converge, right? This is an increasing bounded sequence. This is a decreasing bounded sequence, right? By the what theorem? Got an increase, you got a monotonic, I should have said monotonic, by the monotonic sequence theorem, right? By the monotonic sequence theorem, both converge. Right? Both of these guys are gonna converge. Right? Right, both converge to some L. And if you look at the difference, right, further, if you look at S2n plus 1 minus S2n, well, that's A2n plus 1. If you look at the difference between an odd guy and the previous even guy, well, that's A2n plus 1. And so what you see is that the limit of S2n plus 1 minus S2n is 0 as n goes to infinity. That is, the two sequences are going to converge. Further, they're going to converge to the same thing. Yeah, so I should have said both should converge to some, maybe L1 and L2. At this point, we don't know that they converge to the same point, right? But now we do, right? The difference between them is 0, becomes 0, so L1 and L2 are the same thing. Everybody get the idea, right? You've got a lower sequence going up. You've got an upper. You've got the odd guys going down, right? We know that they're bounded, so they're going to converge to something. And then we look at their difference. Well, their difference goes to 0. Okay. Everybody okay with each part of that? Each part of that, right? Right. The difference goes to 0 because their difference is A2n plus 1. And the a sub n's go to 0. As n goes to infinity, this thing is going to go to 0. Okay. 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 So this is the idea behind the alternating sequence theorem. What we're going to use it for? Why did we explain it in such detail? What you want to look at, what you notice is that. See. Okay, so that's, let me sort of close that, but let me open up something else. So, where is L? Where is L? So this is, to answer the question, how wrong are we? Right. Okay, so like, if we are, I guess it's sort of, so, okay, so maybe you can see. So here's the question. Okay, here's the question. If you stop partway along the sum, if you stop at like S3, how far are you away from L? How far are you away from L? So here's your picture, right? 0, S1, S2. Suppose we stop at S2. How far are we away from L? Right? Where is L? Well, we know that L is trapped between S2 and S3. Right? We know L is trapped between S2 and S3. Right? Because, you know, L is, we're going to bounce back and forth. L is going to be somewhere between these guys. Right? Well, what's the distance here? What's this distance? What is that number?
L.
No.
I mean,
No. A3. A3, right? Right. This we've gone A distance here, we come back A2, we go forward A3. Right? So this distance here is A3. Right. A3. So S2 is at worst A3 off, right? And you can see that, you know, if we kept on going, right, if we went to S4, if we went to S4, right, S4 would be at most S5 off, right, and so on and so forth, right? So what you see is that Sn minus L is smaller than an plus 1. Right? Sn minus Sl is smaller than an plus 1. Right? And the reason is that, you know, if you have Sn and you have Sn plus 1, you know that L is somewhere between there. Right? L is somewhere between Sn and Sn plus 1, and the distance between them is An plus 1. Right? Right? L is trapped between Sn and Sn plus 1, and the distance between them, right, the distance between Sn and Sn plus 1 is An plus 1. Right? So you know that the distance to L must be less than, at most, An plus 1. Okay. So what does this tell you? This tells you how wrong you can be, right? If you stop partway down the series. So let me give you an example. Here's an example. If you look at the series, summation -1 to the n over 2n plus 1 factorial as n goes from 0 to infinity. Okay. Well, that's going to be 1 minus 1 over 3 factorial plus 1 over 5 factorial minus 1 over 7 factorial plus blah, blah, blah. Okay. This is an alternating series, right? This is an alternating series, and you see that the terms are decreasing in magnitude. Right? Terms are decreasing in magnitude, so this is going to converge. Right? Leibniz's test says this is going to converge to something. So you know it's going to reach some number, and you're wondering what that number is. Okay, and you say, well, I don't really want to do too much work. I'm only going to sum the first 3 guys, and I'm going to take that as my approximation. Okay, so you add the first 3 guys. It turns out that the sum of these first 3 terms ends up as 0.8416 repeated. Okay. And you're wondering, is that a good approximation of this actual number? Right? And you say, well, by what we just said, we know that the difference between this number and the actual number, right, the error, right, the difference between this sum of the first 3 terms and the actual number is smaller than the next term, right? It's smaller than or equal to 1 over 7 factorial. Right? Smaller than 1 over 7 factorial, which is about 0.0002. Okay. So this is a pretty good, I don't know, it's an okay approximation. It's good, I don't know what you would say about it. It's good up to here. It's good up to 0.002. Okay. Right? And if you wanted to get a better approximation, well, you know, if you wanted to get like, I don't know, 0.00000001 or something, you just have to go out far enough until your next term is smaller than that 0.000001. Okay. Okay? Make sense? So this is how you use, this is if you understand Leibniz's test, then you can get some information out of it, right? How big is your error, right? How wrong are you when you stop at a certain point? Okay. Any questions? Any questions? Okay. Okay, I'm just going to say one more thing about these series before we move on to something even more interesting to me, I guess. I don't know, maybe interesting to you too, I hope. Here it is. If a series converges absolutely, and this is not something we're going to prove, but if a series converges absolutely, then all rearrangements of it converge to the same number. Okay, so that is, for example, if we look at this series, okay, this series, right, -1 plus 1 over 2 squared minus 1 over 3 squared plus 1 over 4 squared minus plus, etc. Okay. And if you change the order of these guys, however you feel like, then the series is still going to converge to that same number, whatever that number is. Okay. Okay, so this is what we mean. And the reason is that this series converges absolutely, right? If you take the absolute value of it, you get sum of 1 over n squared, you know that converges by the p-test and the integral test. Okay. Okay. But if it doesn't converge absolutely, for this guy, -1 plus 1 half minus a third plus a fourth minus plus, etc. This guy doesn't converge absolutely, right? This is the alternating harmonic series, right? If you take the absolute value, it doesn't converge by the p-test. Okay. It's kind of an interesting fact that if it converges but doesn't converge absolutely, then actually you can rearrange it to converge to any number you feel like. Okay, but this is not something you'll see in this course. You have to wait until you take Math 131. So after you take linear algebra, you could take Math 131 if this sort of thing amuses you. I don't know. Okay, so yeah, so this is sort of in answer to that question that we had at the beginning. Do you remember when we first started talking about this thing? I put up this thing and we ended up with 2 equals 3 or something like that, right? And the reason was that, in fact, what we were doing when we sort of took this thing and took out that thing over there and then did these sort of cancellations and stuff, that was actually a rearrangement. That was actually a rearrangement. And the series that we were dealing with was this one, right? And so what we were doing was doing a rearrangement, and we ended up rearranging it to some other number. Okay, in case I didn't want to finish this section without leaving you hanging about that question. Okay. 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 So now we're going to go into the next section, last section of the course, power series. Okay. So the idea here is the idea here is so-called decomposition of functions. I had a big yawn. That's all right. You don't have to be excited. I have to pretend to be excited. You don't have to. Okay, no, this is actually cool. I know how to pretend here. Decomposition of functions. So we sort of started this idea with partial fraction decomposition. We didn't really, but the idea of decomposition, you take some function and you express it in terms of sums of simpler functions, right? What we're going to do here is we're going to take functions and we're going to express them as combinations of monomials, right? So, but they will be infinite combinations of monomials. In other words, there'll be infinite polynomials. Okay, these guys are called monomials, in case you didn't know that. Okay, so one thing that mathematicians like to do is take functions and then express them in terms of simpler functions. One huge thing in the world of mathematics and in your world, although you don't know it, is so-called Fourier series, where you take a function and then you express it in terms of sine waves or cosine waves. Okay. Or you take a picture, you express it in some sort of, something like sine waves and cosine waves. That's the foundation of any sort of data compression, like image compression, sound compression, CD players, DVD players, all that stuff is based on this business of taking a picture, right, or taking a video, taking a sound, and then decomposing it into into combinations of simple functions, and then just recording how much of each of those simple functions are in the sound, so that when you put it back in your machine, it says, oh, just take this much of this sound, this much of this sound, this much of this sound, and put it back together, and you get back your original sound, or at least close enough that humans cannot distinguish between the original. Anyway, so the beginning of this stuff for us is going to be so-called power series. Okay, so here's the definition. Any function of the form p of x equals a sub n x to the n as n goes from 0 to infinity, where the a sub n are a sub n are in R, anything like this is called a power series. Power series in X. Right? You see why it's called a power series, right? It's sums of powers, sums of combinations of powers. Okay. Power series in X. Similarly, power series in X. Sometimes people say centered at 0. You don't have to say that, but similarly, if we have something like summation, maybe I should use a C here. C sub n x minus, I use A's. A sub n x minus C, saying as n goes from 1 to infinity, is called a power series centered at C.
What's C?
Where C is a number. So C is some number. So, okay, let me put up another definition first. So this is part 1 of the definition. Part 2 of the definition is this: given a power series, summation a sub n x minus c to the n, the set of x where the series converges is called the interval of convergence. Of the power series. Okay, it's not always called the interval of convergence. Sometimes it's called the disk of convergence, or the ball of convergence. But we're in one dimension. This is Calc 2. We're just in one-dimensional calculus, so it's going to be an interval. If we are in higher dimensions, then it'd be some sort of disk. But for us, it's going to be some sort of interval. Okay. So these power series are functions. Okay. They're functions that are expressed in this way as some sort of infinite series. Okay, right? So the infinite series, where it converges depends on what x you put in. Where it converges depends on what x you put in, right? So it's not going to may not converge for every x. Some x it's going to converge for, and some x it's not going to converge, right? Let me maybe make this concrete. So here's the best example for us. Summation x to the n goes from 0 to infinity. Okay, so this is a power series, right? This is a power series, right? It's a function expressed as some sort of infinite polynomial, right? All of the a sub n here are ones, right? It's a simple one. All the coefficients. These guys are called the coefficients, right? Just like as if it were a polynomial, right? Because it is a polynomial, just an infinite one. Okay. So all the coefficients for this guy are 1. This is a power series. Everybody see that this falls into that bucket, basket. Okay. What's the domain of convergence? Well, the domain of convergence are the x's for which this series converges. Well, suppose I put in 2 here. Do I get convergence? No, right? Summation of 2 to the n does not converge, right? What is the domain of convergence for this power series? Somebody tell me. Right.
Less than or equal to 1.
What's less than or equal to 1?
X.
Yes. So x is less. Well, let's see. S is less than. Is this what I should
less than 1.
Less than 1.
And more than.
And more than
0.
0. Is that right?
Negative 1.
Negative 1. Yes. Now you've got it. Okay. It's like talking to my son. Like, what's 99 plus 57? 999? 1,000? 300? No. 156? Yes. Yeah, I don't understand how my son's brain works, actually. My daughter's brain, I understood pretty well. Right? It's pretty orderly. My son's brain. What's 19 plus 89? I don't know, 200? And then like 10 minutes later, I give him like, what's 1,024 plus something. And he says, oh, it's this. And he's right at that time. So, right. Yeah, anyway. He can't add 2-digit numbers, but he can add 3-digit numbers or 4-digit numbers. That is to say, it just doesn't feel like it. Okay. Yeah. Yeah, our nickname for him when he was a kid was Mr. Random. Mr. Random. Okay, so, yeah, so, right, so we know that this is the geometric series, right? So this is going to converge, this will converge, so it's integral convergence is, right, just -1, 1. Okay, right, the interval of convergence is -1, 1. Right. -1, 1, right? And just, we're not going to use this fact right now, but notice that in that interval, it converges to a function, to a function 1 over 1 minus x, right? Summation of x to the n from 0 to infinity, we saw earlier, is 1 over 1 minus x. Okay. So this is a little bit peculiar, maybe, because 1 over 1 minus x is a function that makes sense on the whole line, right? 1 over 1 minus x is a function that makes sense on the whole line. We have a power series that we can express this function as a power series, but the power series only works on this little interval, right? It doesn't work on the whole line, even though the function is valid on the whole line. Okay, and you see that if we try to express the function outside of here using that power series, it doesn't work. We get infinity. So things are not completely simple. Okay. 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 So another thing to notice is that this -1, 1 was centered at 0. Was centered at 0. Okay. This is not a coincidence. There's sort of there's a theorem that says the following about the form of the domain of convergence. And it says this, given a power series, summation a sub n x minus c to the n, and from 0 to infinity, the domain of convergence must be of the following form. Must be one of the following. It could be just C itself. It might be just C itself. Okay, that's one possibility. Another possibility is that it could be the whole real line. Another possibility, the rest of them have to be the following. They have to be this last category. They all have to be an integral centered at C. And it could be open, closed, or half closed and half open. And these are the only kinds of intervals of convergence you can get. this is kind of interesting, right? Because we just have some power series. We just have some power series, right? And the interval of convergence is where, for what x does this thing converge? Okay, and what we're saying is that if it looks like this, well, it's got to be something centered at 0. It's either the 0 point, or it's the whole line, which is centered at 0, or it's some interval, which is centered at 0. It's got to be like that. You can't have, for example, something like this, right? Something like this and then here, right? It has to be this thing that is, right? You can't have like converges here and it also converges here and maybe also at this point. That's impossible. That's not a possible domain of convergence for a power series. Okay, it has to be one of these forms. So
Is that E or C?
that's a C. That's a C. Okay. Yeah. Okay. So okay, I'm going to explain why this happens. Okay. I don't know if you're going to like this. So, but we'll do it anyway. Why does this happen? That's why I was pausing. I was thinking, are they going to like this? They're not going to like this. So here is the lemma. I don't even know if we used the word lemma before. Have we used the word lemma before? No. So lemma is just like a theorem, but it's a tool, like a small theorem that you use to get a bigger theorem. Okay. Just think of it as a small theorem. Okay. Okay. So here is the crucial lemma. It says the following. So if you have a power series and you have some point, so let's say and so if the series converges at some point x naught equal to 0, so here's 0 and here's some point x naught. If you converge at x naught, then the series converges absolutely in in the interval. It converges in the interval between negative the absolute value of x naught and positive the absolute value of x naught. So here's 0. If you converge at any point, then you converge in this whole range. Okay. If you converge at any point, then you converge in this whole range. Okay, so like if this x naught could have been over here. That's fine. If you converge at that point, then you converge in this whole range. So if you converge at 5, you must converge absolutely between -5 and 5. If you converge at -5, same thing. You must converge in this whole range between -5 and 5. Okay, and this is why we can't have things like this. We can't have things like this, right? You can't have a domain of convergence like this, because if you did, that would say that you converge at this point here, right? But if you converge at that point, then you should have converged at this part too. Do you see that? Right? If I converged here, well, then I should have converged. I should have converged over this whole thing here, right? Okay, so you can't have this sort of like, split up domain of convergence, right? It's got to be one continuous piece. That's what makes it. That's what makes this part true. Does that kind of make sense? Right. Okay. Okay. As a consequence, if you diverge, if the series diverges at some point, it diverges for all x whose absolute value is bigger than the absolute value of x naught. This is just, again, a contrapositive of the previous statement. Right. Here is 0. If you diverge here, well, right? If you diverge at this point here, well, then you must diverge everywhere out here and out here, right? If you diverge at this point, you must diverge everywhere on the outside here. Does the statement make sense to people? Statement, right? So it's saying, right, if you converge at a point, then you converge in this interval. If you diverge at this point, then you diverge outside that interval. Okay. You should have no idea why it's true, right? But let's explain why it's true in the last 3 minutes. So why is this true? So here's the idea. Here is your 0. Here is your x naught, say. Okay. Oh, right. And notice that in this, I'm doing it for these guys centered at 0, but we could do it centered at some other point. Okay. So, right. If this point is. Sorry. Let me just do this first. Okay, so here's the idea. Okay, let's see if you can get it. So suppose that this thing converges at x naught. Suppose this thing converges at x naught. In other words, summation a sub n x naught to the n converges. Why did I say that? I should have just said the second one. Suppose this thing converges. Right, so the power series converges at this point. Okay. Now, let x be such that the absolute value of x is smaller than the absolute value of x naught. So pick some x that's absolute value is smaller than x naught. Right? Pick some x whose absolute value is smaller than that of x naught. And let's consider, right? We hoped to see that the summation of a sub n x to the n converges. Right? Right? That's our goal. Right? We said if you converge here, you converge absolutely here. That's what we're trying to show. If you converge here, you converge absolutely here. If this converges, then this should converge. Okay? Okay, so let's see it. Well, summation a sub n x to the n in absolute values is the same thing as summation a sub n x naught to the n x to the n over x naught to the n. I've just multiplied by the absolute value of x naught to the n and divided by that same thing. Right? Again, I'm multiplying by 1. Right? It's always okay to multiply by 1. Okay. But notice that this thing converges, right? Remember, this thing converges, and so by the divergence test, these terms must go to 0, right? We know by the divergence test that the limit of a sub n x naught to the n is 0. So this will just take 20 more seconds. I'm sorry to keep you over. Okay. Okay. This goes to 0, right? So in particular, eventually it's smaller than 1, right? So eventually we know that this thing is smaller than 1 times this thing. Right? Because this thing is going to go to 0. So eventually this thing on the left, this term is smaller than 1. So this product will be smaller than that. Right? Okay. So we can use comparison test. We compare this guy against the sums of these guys. Right? But what's this? This is the sum of, so direct compare this guy against this guy. But what do you know about this guy? This is a geometric series. And how big is the term? Is it smaller than 1? Yes, because the absolute value of x is smaller than the absolute value of x naught. Right? So this is a convergent geometric series. So we have convergence. This is a convergent geometric series. Okay, that's it for today.